Here's the Lewis structure of oxygen. Notice that there are no unpaired electrons. Oxygen should be diamagnetic. Experiments show that oxygen is paramagnetic. Here's liquid oxygen being poured through the faces of a permanent magnet. It stays there. We need a better theory of bonding. Molecular orbital theory states that the bonds are formed from the interaction of atomic orbitals to form molecular orbitals. Here are the rules for the molecular orbital configuration. The number of molecular orbitals formed is always equal to the number of atomic orbitals combined. The more stable the bonding molecular orbital, the less stable the corresponding antibonding molecular orbital. The filling of molecular orbitals proceeds from low to high energies. Each molecular orbital can accommodate up to 2 electrons. We use Hund's rule when adding electrons to molecular orbitals of the same energy, and the number of electrons in molecular orbitals is equal to the sum of all of the electrons on the bonding atoms. The molecular orbitals are formed by taking the orbitals in each atom and overlapping them. There's 2 possibilities: constructive interference, which leads to a bonding sigma 1s molecular orbital, or destructive interference, which is an antibonding sigma 1s star molecular orbital. A bonding molecular orbital is lower energy and greater stability than the atomic orbitals. An antibonding molecular orbital is higher energy and lower stability than the atomic orbitals. Notice that the 1 electron in each of the hydrogen atoms is put into the sigma 1s molecular orbital. It's a bonding orbital. There's 2 possible interactions between equivalent p orbitals. There's destructive and constructive interference from 2 p orbitals that meet head to head. This forms the bonding sigma 2p molecular orbital and the antibonding sigma 2p star molecular orbital. In the case of the p orbitals, we can also get side-to-side overlap, leading to both constructive and destructive interference. This forms the bonding pi, that is the pi 2p molecular orbital, and the antibonding pi molecular orbital, pi 2p star. In general, the molecular orbital energy diagram is given for the second period homonuclear diatomic molecules shown. Notice that the p atomic orbitals are on either end for each of the atoms, and then the order is pi 2p, pi 2pz, sigma 2px, and then the pi star antibonding molecular orbitals above. This shows the filling of lithium, boron, carbon, and nitrogen diatomics, and oxygen and fluorine. Oxygen and fluorine interchange some of the bonding and antibonding orbitals. This shows the order of energy levels for oxygen and fluorine as compared to the lighter elements in the second row. Notice the change. The bond order is 1/2 of the number of electrons in the bonding molecular orbitals minus 1 number of electrons in the antibonding molecular orbitals. Here we have H2 plus with 1 electron in a bonding orbital, none in the antibonding orbital. 1/2 of 1 is 1/2. That's the bond order. For H2, we have 2 electrons in the sigma 1s, none in the sigma 1s star. Bond order is 1. For helium 2 plus, there are 2 electrons in sigma 1s, 1 in the sigma 1s star, so the bond order is 1/2. For helium 2, 2 electrons in sigma 1s, 2 electrons in the sigma 1s star. The 2 cancels out the 2, making it 0. Bond order. Delocalized molecular orbitals are not confined between 2 adjacent bonding atoms, but actually extend over 3 or more atoms. Let's look at the case of benzene. That's C6H6. The delocalized pi orbitals are shown here. They are perpendicular to the plane. Here's the electron density above and below the plane for benzene. We will show how to fill the molecular orbitals in our exercises in class.